Hello and welcome to this lecture series on operating system. In this lecture, we will learn about virtual memory concepts. Background to this virtual memory concept is code needs to be in memory to execute. So whenever any user program needs to be executed, the entire instruction and data with respect to that program should reside in the main memory. But the entire program rarely used. Okay, so during the course of execution. So for example, error code, unusual routines, large data structures. So entire program code not needed at the same time. So consider ability to execute partially loaded programs. So this facility is to be needed. Okay, so the program no longer constrained by limits of physical memory. So the physical memory is can be lesser space. So what we need to do is which portion of the instruction is needs to be executed. That portion alone we can brought into the main memory at that time. The data also associated with that instructions and then taken back to the backing store, and the next set of instructions can be brought in. So this is going to be the routine of execution with respect to the concept of virtual memory. So in this case, each program takes less memory while running. More programs run at the same time. In this fashion, more number of programs can be executed in the multi-programming concept. So with this, what is that outcome? Increased CPU utilization and throughput with no increase in response time or turnaround time. So the response time and turnaround time will be lesser, so that the CPU utilization is increased. And the less IO needed to load or swap programs into memory. So each user programs runs faster. So here the virtual memory concept, we call it a separation of user logical memory from physical memory. Only part of the program needs to be in the memory for execution. Logical address space can therefore be much larger than physical address space, because to accommodate a huge number of user programs, so the secondary memory or the logical address space can be larger. Allows user address spaces to be shared by several processes. Yes, absolutely. Allows for more efficient process creation, more programs running concurrently, and less IO needed for to load or swap processes. So it is a logical view of how process is stored in the memory. So usually starts at this address 0, contiguous addresses until end of the space. Meanwhile, physical memory organized as a page frames. So a memory management unit must map the logical to the physical address. So this virtual memory concept can be implemented through demand paging or demand segmentation, two types. So this pictorial representation gives a representative structure where the virtual memory that is larger than the physical memory. So if you see here, physical memory has only set of few frames, but in the virtual memory you are having more number of logical spaces to accommodate more than n, and that is n number of processes within the virtual memory. So mapping takes place from the virtual address to the physical address through a memory management concept, that either through paging or segmentation. So this is a backing store which is used during the swapping of the user processes. So the virtual address space usually design logical address space for stack to start at maximum logical address and grown down while heap grows up. So usually the maximum space is allocated, okay, that the largest portion of the memory is occupied by the stack, and then followed by the corresponding space for left for the user processor, then heap, and then data and the entire code. Okay, so the maximum this type of organization maximizes address space use. Unused address space between the two whole, okay, two is whole, that is the corresponding without any allocation of memory space to any process, that is called as whole. No physical memory needed until heap or stack grows to a given new page. So in this case, enables sparse address space with the holes left for growth, dynamically linked libraries, etc. System libraries shared via mapping into virtual address space. Shared memory by mapping pages read write into virtual address space. So pages can be shared during fork speeding process creation, for speeding the process creation. This is a schematic for shared library using virtual memory. So uh, these shared pages, that is a corresponding memory portion, is shared among two processes. That's why we call it shared library. Concept of demand paging. what is that idea is to bring entire process into memory at load time. So that is a basic concept. Only when it is going to be utilized, that time alone, the corresponding user process is getting into the memory, loaded into the memory, or bring a page into memory only when it is needed. So only when it is needed. So less IO needed, no unnecessary IO, less memory needed. In this case, faster response and more users. So this is similar to paging system with the swapping. Okay, so that is it indicated in the right hand side. Okay, so program A was initially there using during the course of execution, and after the execution it is swapped out, or if it is waiting for some IO, then it is swapped out, and a new process B can be swapped in. So in this case, more a number of processes can be swapped out and swapped in during the course of execution, so that the memory utilization, the CPU utilization is increased. So pages is needed. So we need to reference it. The user program references or requests for the corresponding frame page. So if it is gets the invalid reference, then it is aborted. Okay. So if it is not in memory, then we need to bring that particular page from external, that is virtual address space to the physical address space. So what is called as lazy swapper here? Never swaps a page into memory unless page will be needed. So that we call it as lazy swapper. So it is delayed until it is getting needed. Okay. The basic concept here it is with swapping, pager guesses which page will be used before swapping out again. Instead, pager brings in only those pages into the memory. So here the question is how to determine the set of pages. So here is the corresponding memory management unit, which functionality there the concept of demand paging comes into picture. So if no pages needed are already memory resident, no difference from non-demand paging in this case. So if page needed and not memory resident, need to detect and load the page into memory from storage in this case. So there is a valid or invalid bit that is implemented. With each page table entry, a valid invalid bit is associated. Okay, so V means it is in memory, memory resident. I means not in memory. So the invalid valid bit is set to I on all entries. Okay, so this is how the corresponding frame page table will look like. So the valid bit either V means it is in the memory, I means it is not in the memory. So during the MMU address translation, if valid invalid bit in page table entry is I, then we call it as a page fault. That page fault means the requested memory is not, that is requested page is not available in the main memory. So that is called as page fault. So if you see here the page table, this is a page table where some pages are not in main memory. So here if you see here, only 4, 6, 9 are there. Okay, 4, 6, 9. So whenever the reference to the page table given by the corresponding user process, if 4, 6 and 9 is the reference, then no problem. Okay, so because valid bit is V here. If any other reference comes, then it is I, so that we need to bring that particular page from the secondary storage to the physical memory. So this case page fault occurs when a reference to a page, first reference to that page will be trapped with operating system, which is called as page fault. Operating system looks at another table to decide. So whether it is invalid reference or just not in memory. So it finds the free frames, swap the page into the frame via scheduled disk operation, then resets the table to indicate page now in memory. So that means the validation bit is now V, and restart the instruction that caused the page fault. So this is the diagram which explains about the steps in handling a page fault, how the page fault is handled. So if you see, the load M is the corresponding reference or the user program request. So the reference is now given to the page table, and if you see that reference, the valid bit is high, which means that is not in memory. So the operating system, a trap is initiated, interrupt is initiated to the operating system. Now the operating system understands that the requested page is not available in the physical memory, so it goes to the backing store. That is the third step. So it brings that page into the from the backing store to the physical memory. So before that, it identifies one of the free frame here. That happens in the fourth step, from backing store to the physical memory, right? So once this new entry is made, that should be stored, or that information is to be kept in the page table. So resetting the page table with the information, now the valid bit will be V, set to V during the reset process. That is the fifth step. And then the sixth step, the corresponding instruction will be restarted. In this case, when it is restarted, the page fault will never occur because the corresponding requested frame now it is available in the physical memory. So this is the 6-step process during the handling of page fault. So we will continue the further topics in the next lecture. Thank you.